So first I would like to pay my obeisances to both the Maharaji, whose association I always enjoy. So whenever they call me, give me an opportunity to speak, I never like to miss it. And good evening, everybody. So today my talk is mathematical and spiritual spaces for perfect understanding. When I say the spiritual spaces, of course, this word is a little confusing because often you will be confused with the things like Bacchant or things. But I'm not talking about that spaces. I've taken these spaces, mathematical spaces concept, added this word spiritual spaces also. So the concept I'm generating like mathematical spaces, spiritual spaces, quite generating the same based on similar kind of axioms. So today my talk is abstract of my talk is we know that mathematical spaces are difficult concepts. Generally, we assume that says for researchers who are working in the abstract field of mathematics is a quite complex. So often even mathematics students also they study this concept in their postgraduate level. So in this presentation we'll discuss how response of very simple problem of classical mechanics cannot be obtained with the help of Newtonian and energy approach. That is, we learned basically the Newtonian approach and energy approach, but you'll see that very simple problems we cannot solve using this approach. Okay, because these problems are very rare, so we rarely come across such kind of problems, and we need the concept of Sobolev and Hilbert spaces to solve such problems. And we'll see that if these mathematical concepts are properly implemented, then many real life problems can be perfectly solved. This is a theme. In fact, these concepts are already used in ancient spiritual philosophy of India. Concepts of spiritual spaces will lead to complete understanding of life and its purpose. So this is the abstract of my presentation. So this is my very favorite slide, which I always like to show. So first let us try to understand it, those who are new. What normally we do, we have some simple things like calculation, numbers, etc., which I put at the bottom. I say mathematical model. So if you develop the mathematical model and if you try to understand something like scientific laws, you cannot understand. Scientific laws like Newton's law, thermodynamics laws, or quantum mechanics laws, they are observed. They are not understood by mathematical methods. Of course, mathematical methods helps to understand it, but they are basically like thermodynamics laws. We observed heat flows from high temperature to lower temperature, second law of thermodynamics. And if you know all the thermodynamics laws, Newtonian mechanics, quantum mechanics, electromagnetism, etc., you cannot form a matter, by just using your concept. You have to observe, like you observe gold, oxygen, or whatever. The matter you observe. You cannot, by using these laws and mathematics, you cannot conceptualize. And if you know the matter, you cannot say that there exists soul. You cannot, by using just simply logic, matter, scientific laws, mathematics, you cannot prove that there exists life. Life you are observing. Am I right? So what you are doing is that when you are going from lower level to higher level, you are just observing. You are at this level, then you go to next level, you are observing. You are not able to prove it. You go to this next level, you are not able to prove anything. You are just observing. From matter also, you are not going to prove anything. You are just observing that there exists a living being. And when you are not able to observe that absolute truth or supreme being, you cannot prove it. Can you prove it? It's just not possible. This is what you will feel. You cannot prove that, okay, the supreme being will be something like this. Krishna will be like this, he'll be wearing peacock feather or whatever. It cannot be proved. Okay, so here things is like this. We are living beings and we can understand the lower concept. We can understand the matter, scientific laws, mathematical models, but you cannot go to the higher side. Okay, but here by using mathematics we want to understand the absolute truth. So up to what extent we can understand? This is the question. Okay, we are trying to understand the absolute truth or supreme being, but up to what extent we can understand? This is the question. And if we can understand, then what should be the method? Okay, if we understand something, if we can prove something that there exists a supreme being, then up to what extent we can prove that, okay, Krishna will be like this, Lord Krishna will be like this, or Lord Ram will be like this. To what extent we can prove? This is the question. What should be the approach and to what extent? Now, there's another problem also. Now, sometimes after seeing also you cannot understand truth. For example, in case of quantum mechanics, we observe, we do experiment, but still there's no proper concept. Like for example, there are many theories developed in quantum mechanics. They are all observing the same thing, same wave particle duality, etc. But then there is so many concepts developed, different theories developed by different great scientists. So it means that even if you see the things, then also you cannot understand in some cases. Okay. One thing is that you cannot see. Another thing is that even after seeing also you are not able to understand the things perfectly. So, and there another problem is that many times our observations are not complete. This is very common. So either sufficient facts are not available, or this world of three-dimensional visual space and time cannot provide them. This is another problem. We can see only three-dimensional visual space. So that is not. So then how to find the truth or get correct understanding? So here is a quote from Professor Abdul Kalam. He says that you can observe a thing or not depends on the theory which you use. It is the theory which decides what can be observed. Okay. So does it mean that theory has an upper hand over observation? Okay. So means what you see depends on your theory. This is something interesting. Now let us come to the mathematics. So we know that mathematics is doing many wonders. For example, you have one governing equation, many physical meaning. Means you have one differential equation and then the physical meanings are different. Different condition you can apply and then it gives a different meaning and solution. Then there are other interesting example is knot theory. Knot means you are putting the knot on the rope. So they developed the theories using topology. That's called topology. And they found that the DNA structure concept is very similar to what they are getting from knot theory. They are two very different things. Knot theory is developed separately for different purpose. Then they found that DNA structure is getting that information from that knot theory. And then Heisenberg uncertainty principle, which is a purely mathematical concept. And then they found that it's applicable in time frequency analysis or mass momentum relation, etc. Position momentum relation. So this is something very interesting. You develop something for a very different purpose, and then you find that physical system is following that mathematics. Now, if we see the mathematics, we can categorize in two parts. One is the applied mathematics, another is pure mathematics. Applied mathematics gives the quantitative analysis, like numbers, figures, etc. You get the curves, that okay, the behavior will be something like this, or the numbers. Whereas the pure mathematics, it just gives the qualitative analysis, that solution will exist or it will not exist, or in this space it will exist. It is based on logic. Pure mathematics is purely logic, and this applied mathematics is more number. So most of the time we work on applied mathematics, particularly the engineers or scientists, they use mostly the applied mathematics. Pure mathematics, they rarely go in that. So here the pure mathematics is more based on logic. Okay, it's a more logic. And another term which I am using is logical continuity. So logic itself is a continuous thing. If logic is not continuous, then you will say that your logic is wrong. Am I right? If I say something and then abruptly change and then say something, then you will understand that there is some abrupt change. Then you will say that your logic is wrong. So logic is continuous. Logic has to be continuous. But here I am using another term which I am calling as logical continuity. Why I am using this word and I am emphasizing it, you will understand it. So before going to this, let us understand what is logic. I said logic is a set of statements consisting of rules and accepted observations, that is facts, directed for new finding. So when you use the logic, you have that, okay, you want to find something, okay, or you want to defeat in the chess, for example, you want to defeat the opponent in chess, something like this. So you use the rules. Chess has some rules and some observation. So logic is basically the set of statements for some directed new finding. So what is the pure mathematics we do? Okay, we use the higher dimensional science. Pure mathematics, it is based on logic and generalization of basic mathematics. We'll see how. In higher pure mathematics, we try to understand the spaces which is beyond three-dimensional spaces. Okay, and we'll define the vector. Vector generally we use I, J, K. We use the vector I, J, K, normally. So that vector, of course, for engineers it is very convenient to use that vector. Vector means something like V1I plus V2J plus V3K or something like this. This is what we learned. Vector means something which has magnitude and direction. But in mathematics, okay, you will see that this definition has some flaws. Okay, this definition has some flaw. What is the flaw? When you say that the vector means it has a magnitude and direction, then what is the rotation? Rotation is a vector or a scalar or what? So often people will be confused because rotation also has a direction, anti-clockwise or clockwise, and magnitude. So it should be vector, but it is not vector. Okay, so mathematics, or example, length. Okay, in three-dimensional you define the length, it's fine. But when you go to higher dimension, how will you define the length or angle? So generally we engineers and scientists, often do not take interest in all these things because for most of our problems can be solved in three-dimensional spaces. Okay, so we rarely go for such abstract concept. We feel that these are not very useful. Okay, for most of the problems, this is not required. So for particular problems, we may find the solution, engineers, scientists. But there are some problems. There are some problems whose solution you cannot find using these simple concepts. They are simple problems, but still you cannot solve those problems. That is the interesting part. I'll show you that simple problem. So before I go to this concept, generalized concept of vector or length or angle, I have to define what is the mathematical space. Okay, because I'm using this term very frequently. So we all know this set. Set means some elements, like myself, books, a computer, table, fan, dogs, etc. And then we form and say that this is a set A. Okay, this is a set and a collection of things. Or we say that X, such that X has citizenship of India. Means all Indians, they say that we call that set as an Indian. So when we define certain condition or axioms, then we call a set as a space. Okay, set with axioms. Means you put some certain axioms. Axioms is what? Can anybody tell what is axiom? What is axiom? Some statement which we accept, without any question, without any self-evident.
Accept them as self-evident.
So we just accept that statement. This is true. We all accept that this is true, without any question. So that is axiom. So when you put certain axioms and form with that axiom some set, then we call that space. Okay. So space is not something like our spiritual spaces. It's a very simple set with some axioms. Now here, when we define the vector, so we say if we define the vector spaces, anything which belongs to this vector space is called vector. Okay. So these are the axioms. That it should satisfy u plus v is equal to v plus u. Okay, so you will say that in every condition, because you have worked mostly in the real number, integer numbers, you'll say that u plus v is always v plus u. But in case of angles, you cannot say that if you rotate 30 degree clockwise and then 40 degree anti-clockwise direction, then it is not that if you reverse it. So the rotation will not be vector. It will violate this axiom. So it will not, u plus v will not be equal to v plus u. So these are the certain axioms. Anything which is satisfy these conditions will be called vector. So this is a vector. Okay. And if you see the f is a function and g is a function, another function. Okay, f and g are, let's say f is a function like this. Say this is a function and g is another function. Okay. This is also vector. Okay, this is also vector because it will satisfy these conditions. So here you see the things are generalized. Okay, vector is not just this one. This is a special case. You will find that this is a very special case of this vector space. Okay, now what is the advantage? You will see later. Similarly, the length. How will you define the length? Say in case of 3D, when you say that if you want to add, this case length of the vector, I will write it like this, length of v. So we will say that this is something like v1 square plus v2 square plus v3 square. Am I right? Suppose you are working in 4 dimension, then how will you work? Can you write v something like ijkl, v4l? Can you write like this? Probably you cannot. You cannot write like this because these are, I'll tell you, these are orthogonal basis function. But you can write the vector v as a set like this, v1, v2, v3, v4. This is possible. Okay, this is a vector. You cannot use the ijk, the basis vector. Of course, this ijk will be replaced by something else, which will you'll learn later if you go in this. And what about the length? How will you find the length? Can you write the length of this v? Another v, you can say the v bar. If I say the v bar, length of v, we represent it like norm. We call it. This is called norm. So can you write it like this? v1 square plus v2 square plus, like this, and then square root of this. Can you write it like this? Yes, you can. If this is called norm, the norm is a generalization of length, and if it is satisfying these axioms, then we say that this is the length. So you can go in any dimension. You are not restricted to 3 dimension. You can go to any dimension. In fact, this is also, you can write, find the length. Of course, there are many ways of finding the norm. It's not a single way. There are many ways of finding the norms. So this is another subject, It means that, and then this case which we know, is a very simple special case. Okay. Similarly, if you go to this another term is called inner product, which is a generalization of angle. Angle, if you want to generalize, then anything, any function kind of thing which is satisfying these axioms, they call inner product, and it is a generalization of angle. Means the angle you can get using simple cases, like in this case, you can get the angle cos theta in terms of cos theta. Okay. So, what you are doing? You are using axioms to generalize the concept of vector, its length, its angle. So, what is the advantage of this? Advantage is that you can understand the higher dimension. And the simple 3-dimensional Euclidean space is a very special case. Okay. So, whenever you want to understand anything in higher dimension, this is very much required. These concepts are essential. Now, there are some more concepts are there, like Cauchy sequence or convergence. These concepts are there. Complete space you have to define. It's a little complex. Then you define a Banach space, which is a non-linear space, which is complete. Complete definition is given here. How it is complete means the limit should exist. It should. And then Hilbert space. Hilbert space means if the length is given by the norm is given by the inner product, and the space is complete, then it's called Hilbert space. Now here the concept is really confusing. It's very difficult. You will feel that particularly initially you will find it very difficult. But then the Euclidean 3-dimensional Euclidean space is a very special case of Hilbert space. Hilbert space is infinite dimensional space, and Euclidean space in which we engineers or scientists most of the time work is a very special case. Okay, here I've said the same thing. Now I'll go a little more because I am going to use it. There's a concept of distribution theory. Of course, these are very, very difficult. Not even the postgraduate level they teach. They basically, those who go for research in this particular area, they study. But it's a very important theory where you get the concept of weak derivative. I mean, something function which cannot be differentiated. Then how to differentiate it? Okay, so there comes the concept of distribution theory. And then with this distribution theory, the normal derivation, you will find that is a special case. Distribution theory is a much more generalized concept, is a most generalized concept. The all other concepts are very special cases. And with this weak derivative in distribution theory, you get the concept of Sobolev spaces. Okay, so you see here, you are generalizing the things. Okay, using what? Using axioms. Axioms, you are creating these spaces and you are generalizing the concept. And all the concepts which we study in our engineering or sciences, they are very special cases. Particularly, most of the time we are interested in solving the differential equation, because differential equations generally governs the system behavior, particularly if it is a continuum. So all the continuum system behaviors are governed by differential equations, and if you have to solve those differential equations. Most of the time you have to solve these differential equations. So here, what these Hilbert spaces are providing, they are providing the basis functions. Basis functions like I, J, K. They are basis vectors. They are called basis vectors. And like Fourier series, you have a sine and cosine terms, they are basis functions. So these provide the basis functions for interpolation and or extrapolation. This space provide necessary continuity for logic. Here I am emphasizing this part. Otherwise we miss it. If we don't select the proper space, then we will miss the continuity for logic. And this is very essential. I'll discuss it later you'll understand it very clearly when we discuss about the spirituality. Why the continuity of logic is essential and why the particular space is necessary. And they provide the idea of limit. That is the best result. This is the limiting point. Normally when we know the result, we can say this is the solution. But most of the cases, we do not know the result actually. What is the God? We do not know. So we have to guess, by some mathematical means that, okay, this is the limit. So that type of limit you get when you work in these spaces. So, in the domain of mathematics, logic is perfect because it always gets proper space for its continuity. This is very important. Okay. Mathematics, we get the proper space. So some are trying to find God by using mathematics. It's an interesting thing. But we question it also. Can they find it? Then, can we understand everything using existing mathematical spaces? This is a question. We have a lot of spaces, Riemann spaces, like Maharaji was telling. So, Euclidean space. Now I have told you the Hilbert and Soule spaces, etc. So, can we understand everything using the existing mathematical spaces? The answer is what I believe is no. Not with the existing mathematical spaces, which ignores many facts. Like yesterday, they were saying that the consciousness, they ignore it. So when you are ignoring certain facts, how can you understand? This is what we'll see later. Now let us take a very simple example, and then you will understand the importance of these mathematical spaces. उस परमानेंट मार्कर तो नहीं है, परमानेंट मार्कर था क्या ये? ये लिखा हुआ है परमानेंट मार्कर, अभी देख रहा हूँ मैं, नहीं होगा. नहीं, ये गलत मार्कर लगा दिया था इसमें. थोड़ा सा ये उसमें किसी ने परमानेंट मार्कर लगा दिया, नहीं होगा. देखो, नहीं आएगा.
और फोटोग्राफर is asking for आप खाली राइट कीजिए, he wants picture.
Okay, so let us take a simple example. Bar means a simple, this is a bar. Okay. And this is a straight line. No? I'm not good in drawing, even though I'm a mechanical engineer. So, when we say that uniformly distributed load, it means that it's something like this. Your load is like this. Okay, and of course, you can get this differential equation easily. Because you can take this section like yesterday Maharaji was telling, and derive this this portion, let us say, is a strain du or dx, multiply it with EA. So this will become like stress. Okay. And when you multiply with the area, then it becomes distributed force. And when you again differentiate it, then you will get force per unit length, F. Okay. So this kind of equation you can derive, this Newton in mechanics. Now, there's another problem. Let's say this is a bar, and you'll apply the load like this. Okay, one end. How will you derive this equation? You cannot use this concept. You have to use the energy principle, because then this is the energy, strain energy, and then work done. And using this, you will get using energy principle, you will get the equation in the form of integral differential equation, and then you can solve it. This is fine. This is a simple example. If I take little more complex, I take a membrane. This is a membrane. Okay. Here also I can use energy principle if it is a distributed load. Okay, and I get the equation like something like this, du or dx Poisson's equation. This equation we get dy square is equal to f. F is the distributed load. It's fine. Now if I make this as a concentrated load here, just one concentrated load, so what will be the f? Here in this case, in this particular case, you can say it is like a delta f, concentrated load at particular point, let's 0. This is O or whatever you say, del 0 f. This del 0 f is very well defined in one-dimensional case. Okay, so energy principle, no problem with this delta function. Here also you have a delta function. But can you solve this problem using the energy principle? The answer is no. There are people who solve it, but the mathematics understand that this is wrong. And there is a very complex theory on this, which you get from Sobolev spaces and distribution theory.
How does one know which one to use? Energy principle or?
See, the simple problems we get the Newtonian. Little more complex we use the energy. But even though this problem also looks very simple, but it is a two-dimensional. So even the energy principle will not work. Here you have to use some more complex theorems, which says that the load function should be a particular space. Okay, this is something like this. Therefore, one-dimensional, this is fine. For two-dimensional, the load function should be a particular space, a Hilbert space. If the differential equation is from this equation space, then the load function should be from this space. There is a theorem. So it is not as simple as you think. Even though it looks, the problem is very simple. There, in fact, in my PhD viva, the examiner was from IIT Kanpur, and he asked me this question. I was solving this type of problem. He said, "Can you use the concentrated load?" So I was not knowing answering the final viva. So my guide shook his head. So I said, "You tell yes." So I said yes. But later I realized that I was wrong. Because when I understood the work of people like Gilbert Strang, MIT professor, etc., then I realized that this is not so simple. It's not so simple. There are many engineers who make this kind of mistake. See, the problem is this. If you are solving this problem using any numerical methods, let us say finite element method, you give the problem, you give the input data, you will get the answer. So if you do not know the actual things, then you will say that this answer is correct. The numerical methods will give you the answer. But in some cases, like once I was examiner in one PhD student in MNRC, and he did the same mistake. But then he was not getting the answer in every case. For example, when he put the concentrated load at the center, he is getting the answer, but when he shifts, he doesn't get the answer. So I said that you are doing mistake. This is the problem. So though the problem is very simple, but the answer is very complex. So this is the some of the problems which you need the concept of Hilbert spaces or Sobolev spaces.
One slide before.
Pardon?
One slide.
Back.
God.
You are talking about this?
God slide. Next. Yeah. Sir, using mathematics to find God. In mathematics, we do many mathematics which have no relevance in the physical world. So, just by using mathematics, what you are...
No, actually, I want to say that, see, the mathematics is giving you the perfect logic. Like I said, that axioms, etc. You are creating the space, you are applying the logic, you are developing a lot of theorems, etc. Okay, you have developed, that's fine. Now, we have to adopt that concept. Using the axioms, we have to create a space. And with the space, we have to develop the theorems. Like the Hilbert space and etc. They have their theorems. And using those theorems, we will be able to understand perfectly the things. Otherwise, we will not be able to. If we want to understand the simple methods like Newtonian mechanics or energy principles, we cannot understand it. Even though it looks very simple, but we cannot understand it properly. So the best way of understanding anything is that you use the axioms, create the space, develop the theorems, and then try to understand it. This is a very difficult process, but this is what is used in our scriptures that we will see. That example we have shown, bar example. So what do scripture says? That's what this question. So first axiom is that we are Brahm. Athato Brahma Jigyasa. So this is axiom. Why axioms? Because we all accept it. There is no more denial. Nobody can say that we are not Brahma, soul. We cannot, even Christians cannot say that they are not soul. Or Muslims cannot say that they are not Ruh. So we all accept it. So this is axioms. So using this axioms, you have to create a space. Okay, this is a soul, so we should not kill it. This is a logic. Okay, we should honor the other soul. There are many axioms. Bhagavad Gita is full of axioms. For example, when you say that Rajasic, Tamasic, Sattvic, mode of goodness, mode of passion, mode of ignorance. These are the axioms, and you are creating this space. Suppose you are in mode of goodness. You have your logics. I am in mode of ignorance. Then even if you want to say something, I will not be able to accept it. Because you have one space, you have your own observations, you have own facts. I have my own observation, I have my own facts. So your logic will never be satisfy my observations or facts. For example, you will say that don't cheat. I am in ignorance. I will say that when I cheat, I enjoy. So why should I not cheat? Because I am in the mode of ignorance, I enjoyed that. So your logic will not fit it. So your space is different, my space is different. So when your space are different, your logics will be different. My space is different, so my logic is different. Okay. So my observations are different. Logic means what? You are observing something, you have some rules, and then your logic is satisfying those. Logic is satisfying those observations or facts or whatever. So this is another important concept. The Rajasic, Sattvic, Tamasic, and Sattvic, Rajasic, Tamasic. They are all the spaces. And theorems, if we divide it, instead of dividing like normally we divide it like Hindu or Muslim or Brahman, Kshatriya, Shudra, etc. This is not the proper way of creating this space. Of course, this is what practice. But the Bhagavad Gita says that the best or the only method is that you have to classify the people as Sattvic, Rajasic, Tamasic. Not something like I am Brahmin or I am Kshatriya, my birth. This is what it says. So this is based on axioms, certain axioms. Then another axioms are like man, buddhi, ahankar. Okay, what is man? Can you identify in the brain that this is a man? Or puncture it, then so that I will be always happy or always distressed, something like that? You cannot do it. Man is something like you observe. Everybody observe that there is something which always tries to enjoy. Ahankar, we all know that. This is what we want to prove ourselves superior than the others because of the ahankar. Buddhi, we want to prove something using this ahankar, ahankar. So in fact, man, buddhi, ahankar are like mass spring system. Mass spring system. You have this system, for vibration. Mx double dot plus Cx dot plus Kx is equal to F. Okay. So if I say that man, buddhi, ahankar is something like this. The spring is like man. Okay. This mass is like ahankar. You can say like this. And this you can say something like buddhi. Okay. So all our dynamics is governed by this. अहंकार में जब भी फोर्स लगेगा ना, इस पे किसी ने मुझे चोट कर दिया कि संदीप कुमार तुम्हारा लेक्चर तो एकदम बेकार था, I will be very much hurt. Am I right? So I will start thinking something different. So as you strike on ahankar, force lag gaya. So then my dynamics will be disturbed. All my dynamics, if ahankar is large, very big ahankar, always be stressed. You can understand it. Or I will be always stressed because of the load. And then this man will be break. Load will be there on the man. The spring will break. So you can see that this These are axioms, but they are perfectly giving the dynamics of not only this birth, this life, but constantly birth after birth. So this is another form of, I believe that Bhagavad Gita uses axioms. So in fact, if you see all our literature, they have used axioms. They have observed something which everybody accepts without questioning. And using these spaces and axioms, you can understand many things, the highest level of concepts. By simple observation, you cannot understand. By using these axioms, you create the space, and in that space you apply the logic, and then you can understand everything. Okay. So thank you.
Thank you, sir. So any question to the speaker?
I think very nice, sir. I think it's very good. I have two small humble requests. One is, we would like that this model of your spring comparing mind, intelligence and policy of the anchor, if you can later elaborate it in a form of either at least in 2-3 slides and all, I think it will be nice for all of us to more relish it. This
I will think of
I got your concept, but let it come out more nicely, more in a form of a...
I can tell little more about this.
Yes.
So I was talking this with my professor, and he said that there are two types of, whether you take the mass like this. This is I'm not taking a buddhi, let's say a damper, just using this, and you use this. Sorry, or this one. Let's say mass is on the downward side, okay, and here it is upward side. So this is the baseline, okay. So if you see that here in this particular case, I just jokingly I said that if your mind is like this and you have anchor, you will be always stressed. Okay, but here you are going away from the supreme being, baseline. So you will break here. It will break. Spring will break because of the load. But in this case, the spring will not break. It will be compressed. It will be slow and damped, but it will not break because of the anchor. Of course, the dynamics equation will be same. Both the cases, if the spring is same, the man is same, anchor is same, equation will be same. But in one case, if you are going away from God, you will break. Other case, if you are going towards God, you will not break. So I just said like this. So I know it seems to me okay. This logic. Yeah. So.